Back to our worksheet problem. So we have a ball bouncing on the floor. We're taking plus y to be up. And that's important because we're asked about y impulse components, and so it's important to know which way is plus y. Object moving down at 2 meters per second just before contact, contacts for 1/100th of a second, and then leaves at 1.8 meters per second. What's the net y impulse component given to the ball during the bounce? Well, that's from two different sources. There is a contact force pointing upward that is giving a positive impulse to the bouncing ball, but the weight force is pulling down on the ball, so it's giving a negative y impulse. The net impulse is the sum of all those, but we don't have to calculate it directly because the impulse momentum theorem relates the net impulse to the change in the momentum of the object. So in this case, I can calculate the left-hand side by instead calculating the right-hand side. That's the mass of the ball times the final y velocity minus the initial y velocity. And we know those. In this case, the final y velocity is plus 1.8, and the initial y velocity, since plus y is up, is minus 2. We've got to keep track of those minus signs. These actually add together to give a plus 3.8 there. 1.14 Newton seconds is the net y impulse delivered. Problem, or part B. What y impulse component does the gravitational force give to the ball during the time of the bounce? And in this case, that's going to be a negative impulse because the gravitational force is downward. That's in the minus y direction. And we can calculate that just by the definition of impulse that we use. We said it was the average force, the impulse y component of gravity is the average gravitational y component of the force times delta t. And the average is just the weight because it's not changing, so we don't need to do any averaging to calculate this. So this is just the gravitational weight force y component, and it's a negative y component, so I put an extra minus sign in there, and the magnitude of it is mg. And the delta t is 1/100th of a second, so I multiply all that together and I get minus 0.029 Newton seconds. And notice we can see the impulse momentum theorem at play here. We have somehow been able to figure out the net impulse delivered to the ball is just over 1 Newton second, and the impulse delivered by gravity is a very small fraction of that, and so the impulse momentum theorem would say we could just ignore this, but in this case you happen to be asked to calculate it, so we are calculating it here. But the impulse momentum theorem would say, look, this is a negligible impulse compared to the one we're going to calculate now, which is the impulse delivered by the contact force. What y impulse component does the floor give to the ball during the time of the bounce? And in this case, we don't know what the floor force is. It's rather complicated. When the ball has compressed just a little bit, the upward floor force is going to be kind of small. When it compresses a lot, the upward floor force will be rather large, and then it will get small again as the ball decompresses. So to calculate that impulse directly like this would be really hard. We'd have to do one of those areas under the curve kind of things. But the idea is we already know the net impulse y component, and we know the gravitational impulse. That was the part B answer. So the net is nothing but the gravitational impulse y component plus the floor impulse y component. We know these two, so we can solve for the third by subtraction. And so we'll just take the answer to A and subtract off the answer to B, and that gives 1.17 Newton seconds. So notice that's very close to the net impulse. So we're saying, we can kind of ignore this thing and pretend the net impulse is the same thing as just the contact force impulse. That would be the impulse approximation in this problem. We're not really applying it here. We're seeing that it's justified. Part D, what average y force component does the floor exert on the ball during the bounce? So we can use our previous result of 1.17 Newton seconds to figure this out. That 1.17 Newton seconds is the impulse, and that's equal to the average y floor force component, y component, times delta t. We know the delta t is 0.01, so to solve for this, that's the answer we're looking for, we just divide by 1/100th. Dividing by 1/100th ends up multiplying this thing by 100, and that gives 117 newtons. What y impulse component does the ball give to the floor during the bounce? Well, in this case, we already calculated the y impulse that the floor gives to the ball, and because the force of the floor on the ball is equal and opposite to the force of the ball on the floor, if we want the impulse given by the ball to the floor, it will be equal and opposite to the impulse given by the floor to the ball. Floor to the ball gave 1.17, so the ball to the floor y component impulse is minus 1.17. That's just Newton's third law. And then finally, what average y force component does the ball exert on the floor? Well, we already have the floor on the ball is 117 newtons, so I know the ball on the floor must be minus 117 newtons. The floor is pushing up on the ball is pushing down on the floor, and that's a negative y force component. Okay. Here is a voting question. A ball is dropped from rest. It's supposed to say a ball is dropped at rest from a great height, I think. After reaching terminal speed, we continue to watch the ball for 5 more seconds as it continues to fall. So it's falling down at terminal speed. During these 5 seconds, the greatest magnitude impulse imparted by the ball is from the gravitational force, the drag force, or none of the above. Those are the only 2 forces at play here. So if they're nearly equal, then answer C. In this case, the correct answer is C, and that's from the impulse momentum theorem. In this case, if the thing is falling at terminal velocity, we take initial to be the beginning of the 5 seconds, final to be the end of the 5 seconds. Change in momentum is 0 because it has the same velocity at both points. So the net impulse delivered to it has to be 0, and that comes from the gravitational force impulse plus the drag force impulse, and so they've got to be equal in magnitude if they're going to cancel out. Let's stop there.